In an earlier video, I had alluded to the fact that if I put two objects of different temperatures in contact, thermal contact with each other, there will be an exchange of thermal energy. We saw that that's a heat transfer, and that the temperatures would change as a result. So to quantify this, we'll start by thinking about having just a mass of material here. And we'll say that we have an inbound transfer of heat, like so. And so schematically, when I draw these double lines with an arrowhead, that's referring to a heat transfer. Now, if it's a inbound transfer, Q will be positive. If it's an outbound transfer, Q will be negative. But in any event, what we've seen is the temperature will increase. Now, experimentally, what has been found, and we will eventually derive, is that as long as there isn't a phase change, the increase in temperature is directly proportional to the amount of heat the amount of the heat transfer and the mass, which we'll write as capital M, of the substance, and it also depends on the substance itself. So to characterize all of that, we define a quantity called the specific heat. It's also known as the specific heat capacity, but most people will just drop the word capacity. So here we would be saying that the heat transfer will be equal to the mass times C, our specific heat of the substance. And this is just a number you can look up in tables. It depends on the details of the molecular bonds, times the change in temperature for our transfer. The units of specific heat, though, we need to be a little bit careful about. They are joules per kilogram Kelvin. So as a quick point of reference, the specific heat for liquid water in the sorts of units that physicists like, joules, kilograms, and kelvins, is 4,184 joules per kilogram Kelvin. Now, if you've seen this sort of thing before in a chemistry class or something, you would also note that that's the same thing as 1 calorie per gram Kelvin. So the 4.184 is coming from the mechanical equivalent of heat. 1 calorie is 4.184 joules. Then we pick up a factor of 1,000 because physicists like to work in kilograms rather than grams. So if you have a whole bunch of specific heats committed to memory already, there's a good chance you're going to need to make those multiplied by 4,184. So all the numbers are going to look an awful lot bigger. Now, that's if you're, so here, M, capital M, is the mass of the substance. And generally when you're working with solids and liquids, this is a good way to go. But sometimes if you'll want instead to be looking at molar quantities. So in that case, we would be saying that the heat transfer is equal to the number of moles times the molar specific heat, which is a capital C, times the change in temperature. So here, typical units are going to be joules per mole Kelvin. And again, if you're used to dealing with this from chemistry class, you're going to have all these numbers will differ probably by a factor of 4.184 because they're 4.184 joules per calorie, and most chem classes would have used calories per mole Kelvin. Now, an interesting little tidbit is while specific heats by mass vary wildly, they tend not to vary so much by molar values in solids. Most solids, with the notorious exception of frozen water, have a molar specific heat of 25-ish joules per mole Kelvin. Maybe like 24 to 26 would be a good band to think of here, or even a little higher, but just in the ballpark of 25. Frozen water, ice, is notoriously high at 37.6. That's sort of the exception, and that has to do with some particular details about the molecular structure of ice. Now, as far as liquids go, there isn't any particular rhyme or reason, but we'll get into why all these numbers are in the ballpark of 25 for the solids later on. Okay. Now, in addition to just changing the temperature of a substance, it's also possible that you could be having a phase change. So if this is the heat, the cumulative heat added, and this is the temperature of something, what you'll usually see is that the curve looks, say, something like this. And these aren't supposed to have the same slope, but these are supposed to be flat. So here's something in the solid phase, then here's where it's melting. Then here's where we are in the liquid phase. Here's where we're boiling. And then finally here we are in the gas phase. Now all of these can have different all these phases here will have different specific heats because, again, the details of how the molecules interact is important. However, it does take energy to change the phase of something. And in an earlier video, we were discussing how if I transfer heat in, I have to add energy in order to to change the bonding structure when going from the solid to the liquid phase or the liquid to the gas phase. So to characterize how much heat we transfer doing a phase change, we define a quantity called the latent heat. And if you've had a chem class before, this will be called, chemists will call this an enthalpy of formation. This is just a difference in jargon, but it's the same deal. If I am going from solid to liquid, we'll say that the heat transferred in or out, so there will be a plus or minus depending on the direction of the transfer, will be the mass times what we call the latent heat of fusion. And so this is if you're melting or freezing. And similarly, if you're boiling or condensing, we use LV for the latent heat of vaporization. Now, you gotta be a little bit careful about the signs. So I actually kind of find like just kind of keeping this graph in mind is helpful. If I'm going from a solid to a liquid, I have to add heat to break bonds. And similarly, if I'm going from a liquid to a gas, I have to add heat to break bonds. I think that's intuitive. Where things can get a little counterintuitive is if I go from liquid to solid, I actually release heat. Heat gets transferred out of the substance in the process. And same if I go condense from gas to liquid, heat gets released from the substance. This, for instance, is why sometimes if you're flying in an airplane and you're coming in for a landing and the pilot has to fly you through a cloud, you'll notice that suddenly you get turbulence. And what's happening there is as you're going through the cloud, water that's in gaseous form is condensing to liquid, and in the process is releasing heat. This makes the air in the area very turbulent, and that gives you the bumps as you go in for landing. If it's bad enough, even with a major jet aircraft, when they're flying, they sometimes have to do a complete reroute to avoid particularly nasty cloud formations that would cause way too much vibration while this condensation is occurring that's releasing heat and making the surrounding air turbulent. So with that defined, we can start to work toward doing an example of how to use these, and the process of thinking about temperature changes and phase changes is called calorimetry. So it's probably best to just work to show how to do this by working an example. So we'll take as an example that I have 0.01 kilograms of ice at 0 degrees C, and I place it in 0.090 kilograms of liquid water. At 80 degrees C. I'll let this come to equilibrium. What is the final temperature? All right. So the way I like to think about systems like this is if I make the system big enough, I can isolate it. By isolating it here, what this means is that I can say that the heat transferred into the system is 0. And then what I can do is I can look at the individual subsystems. So in this example here, my subsystems would be the liquid water and the ice. And then I'll go ahead and identify any heat transfers that are occurring. In this case, the temperature of the liquid water is going to drop in order to provide heat to first melt the ice. And then if we can successfully melt all the ice, we'll have a puddle of water at 0 degrees C that we need to raise up to the final temperature. So what we'll go ahead and do is we'll say that our isolated system is this. So then I can go ahead and write that Q equals 0, but then I can write it as the heat transferred into the liquid water plus the heat transferred into the ice equals 0. So this I is for ice, not for initial. Actually, let's just say ice, just to be super careful here. Now, one of these has clearly got to be negative, but we'll just go ahead and let the math of everything address that. So step by step, let's go ahead and first figure out the heat transferred into the liquid water. Well, that will be the mass of the water times the specific heat of liquid water. I'll put an L there just so we know we're talking about liquid water, times the change in temperature of my liquid water. All right, so that's what I transferred into the liquid water. Now we know that delta T is going to be negative. The water's going to get cooler. This is going to give us a negative number, but algebraically we make it positive, and then the minus signs will take care of themselves automatically. Now, what about the heat that's been transferred into the ice? Well, there are two steps to this process. The first step is we have to melt the ice cube. So we'll have an ice cube at 0 degrees C, and so our first transfer of heat is going to be just to get us to a puddle of water at 0 degrees C. And then we'll be continuing to transfer heat until we get to whatever our final temperature is. So there's a two-step process here. So in the first step, to go from solid to liquid just at 0 both times, I'm inputting energy to break all the bonds. So that's going to be, so I should call that L there for the liquid water. So this will be the mass of the ice times the latent heat of fusion of water. And the reason it's a plus sign here and not a minus sign is that we are breaking bonds. If we were forming bonds, we would have picked a minus sign. And then the next step now is that assuming that we had enough heat available to melt all the ice, I now have a puddle of water at 0 that I have to get up to the final temperature. So I'll just write mass of ice, specific heat of the liquid phase of the water, not solid, because at this point we went from solid, liquid, liquid, like that. So this is in the liquid phase going from 0 to T final. And we'll just say delta T for the ice. That's equals 0. All right. Now let's go ahead and come up with expressions for the delta T's. So this will be mass of liquid water, specific heat of liquid water. This will be the final temperature of both the ice and the liquid water. And then we'll say minus TL for we'll say T initial L for the liquid water. We still have our latent heat term to account for breaking the bonds. And then this is going to be CL. Now, this will be the same final temperature we had before. And for our initial temperature, I'll say T initial for the ice. But I will go ahead and immediately put in that that's 0 degrees C. Now, here's something where you want to be really careful. The deal here is that the specific heat has units that go inversely as kelvins. But we have to remember that those are temperature differences. So if I look here and here, this is in Celsius, this is in Celsius. The temperature difference will be Celsius degrees, and a Celsius degree is a Kelvin. So I don't have to convert my temperatures to kelvins if they're differences. I can just leave it in Celsius and it's okay. So here I'm leaving it as a difference so that I can go ahead and stick in a 0 right away in order to make the numbers easier to compute. Now, if I will say this, if you're ever unsure about whether you should convert to kelvins or not, just do it. It's never a mistake to convert into Kelvin and then convert back out to whatever you need. At worst, you're just needlessly adding and subtracting factors of 273.15 and maybe having to carry additional algebraic terms. But it's never a mistake to convert into Kelvin. But here, because these are temperature differences, I can leave this as degrees C. Alrighty. So with that thought there, I'm just going to say there's a painful lot of algebra. It's actually not that bad, but there's more algebra than I want to think about. And so I'm just going to go ahead and say when you rearrange this to get T final, what you get is T final equals the mass of the liquid water times the specific heat in the liquid phase times the initial temperature of the liquid minus the mass of the ice times the latent heat of fusion over the mass of the liquid water plus the mass of the ice times the specific heat of the liquid water. And I could have probably rearranged this to be a little more cutesy, but I didn't really feel like it. So let's just go ahead and plug in the numbers and see what we get. So I'm going to get that my final temperature for this is 0.090 kilograms times 4,184 joules per kilogram Kelvin times 80 degrees C. And it's okay for this to be degrees C and not kelvins, because remember, this all came from having a temperature difference. And so this will come out in degrees C and it'll all be okay. Again, if in doubt, convert everything to kelvins. It's never a mistake, but this saves some time. Minus 0.010 kilograms times the latent heat of fusion for solid water is 333,000 joules per kilogram. I'll take all of that and divide by 0.090 kilograms, plus 0.010 kilograms times our 4,184 joules per kilogram Kelvin. And that turns out to be 64 degrees C. All right, that's good. What this means is that in retrospect, I was correct to guess that we had enough heat available in the liquid water to completely melt the ice. If I was wrong about that, I would have got a nonsense answer. I would have gotten the final temperature being below the initial temperature of the ice. And that's just what would happen if there wasn't enough heat available to melt all the ice. In that case, if you go ahead and solve it and you get a nonsense answer, then that means you're left, you now know what the final temperature is. It's whatever the temperature of that phase is. And so then usually the question will be how much of it ended up in each phase. But what you would have to do is go back to here and just get rid of this term here, where you transformed the melted water, where you raised the melted water's temperature, and go ahead and say solve for what the change in the mass of the ice is, or something like that. But you always have to do this sanity check. If the final temperature is either above the initial temperature of the hot thing or below the initial temperature of the cold thing, that means you did not completely change the phase of the thing, and then you have to go back and revisit it. Or if you're just being asked for what the final temperature is, the answer is the temperature of the phase that you're stuck in. All right. So with that, I want to start to think a bit more about molar specific heats. For gases. So it turns out that as we saw before, since the work done on a gas depends on the exact trajectory that you have in PV space, it should, it makes sense that the heat required to change the temperature of a gas depends on the process. Because you can have varying amounts of work, because remember, by the first law, delta E thermal equals Q plus W. Depending on the process, the work will be something or other, and that will influence our change in thermal energy. So it turns out that we can't just cleanly write a single heat is equal to the number of moles times C times delta T. Well, you can, as long as it's C for the specific process. So this is the key thing, is it's process specific. Now so here what we'll do is we'll just say if the process is isochoric or isovolumetric, we'll say that that's NCV delta T. And if it's isobaric, we'll say it's NCP delta T. Now we could imagine having other ones, but it'll turn out that these two are good enough. Once we have these two, we'll get pretty much everything that we can get pretty much anything else we need out of these two. But just an interesting bit of experimental data. If you take a look at the noble gases, so we're talking like helium, neon, argon, all of those. It turns out that CP for all of them is right around 20.8 joules per mole Kelvin, and CV is equal to 12.5 joules per mole Kelvin for each of these. And importantly, the difference in the two, CP minus CV, is 8.3 joules per mole Kelvin. Hey, 8.3, that sure sounds like the ideal gas constant, doesn't it? That turns out to be not a coincidence. Even for other gases, CP and CV will vary a bit. For instance, the diatomic gases, they tend to hover, CP tends to hover around 29-ish, and CV tends to hover around 20.5-ish. But it'll still be true that CP minus CV is still 8.3 joules per mole Kelvin. So that seems interesting, and so it seems like it's worth us taking a look at why that could be. So we'll start by looking at an isochoric process. So remember that isochoric is where the volume is a constant. So I'm going to draw a couple of isotherms. So this will be at temperature T. This will be at temperature T plus delta T. And we will go from initial pressure P. And let's just say it's a heating, but it could be a cooling. It doesn't matter. P plus delta P like that. And V initial equals V final equals V. Or just V initial equals V final. Now, we remember that for isochoric processes, because the volume doesn't change, the work is equal to 0. And by the first law, delta E thermal equals the work plus the heat transfer. Well, if the work is 0, then delta E thermal just equals Q. Now, by definition of CV, delta E thermal is going to be equal to NCV delta T. And this turns out to be more general than you might think, because all this is doing is just talking about the thermal energy of the molecules. Any other heat transfers that were required would be for a process that isn't isochoric, would be ones that were to offset the work being done on the gas. So this is just true in general. So for all processes, it's true that the change in the thermal energy is NCV delta T. So then the rest of it is going to be going into work. But that's part of why I was saying that it's not the end of the world. CV and we can get a lot of mileage out of just CV and CP. So now let's go ahead and look at an isobaric process. So again, PV, V, there we go. And once again, I'm drawing two isotherms, one at T plus delta T. Now remember, an isobaric process is one where the pressure doesn't change. So that's a horizontal line in a PV diagram. So here's my V initial. Here's my V final. And we've said that the work being done on the gas here is equal to the area under the curve. Now, since we're going left to right, it's negative the area under the curve. But this will be, the area under the curve will be equal to P times delta V, the change in the volume. Alrighty. So let's go ahead and start thinking about the first law here. So delta E thermal equals W plus Q. Now delta E thermal is always NCV delta T. And this is going to be the work we just saw as minus, oops, dropped a minus sign there, my bad, right there, is minus P delta V. And then by definition of specific heat, this will be plus NCP delta T. All right. So hold that thought for a moment. And if we take a look at the ideal gas law, so we're doing this for an ideal gas, but the result works out really well in general. So we have PV equals nRT. Well, if I'm not changing the number of moles and I'm not changing the pressure, then I can infer that the pressure times the change in volume would be equal to nR times the change in the temperature. So going back to what I had before, I can now say that NCV delta T equals minus nR delta T. Sorry, why did I write lowercase p's there? That was silly of me. There we go. So NCV delta T equals minus nR delta T plus NCP delta T. Well, I can cancel from each term an N and a delta T. And if I rearrange, I get that CP equals CV plus R. Now, when we think of an ideal gas, we're always thinking of the bag of small billiard balls that basically don't interact. And for a billiard ball, that would be a noble gas or monatomic gas. However, this is fine for a diatomic gas as long as the densities aren't too high. As long as the density of the gas is relatively low, it'll still be an excellent approximation to an ideal gas, and it'll still hold that the difference between Cp and Cv is R, and that has been borne out experimentally. All right. So now let's think about, as I'm trying to lay groundwork for coming up with one of the statements of the second law of thermodynamics, let's think about if we can characterize adiabatic processes a little better. You'll remember before, when we were doing the PV diagrams for them, PV. So this is at a higher temperature, we'll say T high. This is at a lower temperature, which we'll cleverly just call T low. An adiabatic process was one that, say if I went from T high to T low, it followed along a curve. And I, at that time, said the pressure was proportional to V to the negative gamma. It turns out this gamma is related to Cp and Cv, but we'll go ahead and come up with that. So to do that, I'm going to have to write the first law in differential form. So taking the first law and differentiating it, you would say the differential of E thermal, dE thermal, would equal the differential of the work, d work. Now here's the bit where I have to finagle for a sec. You'll notice that for the heat bit, I had to put a little bar through the Q. And this is because, remember, heat is thermal energy in transit. So it's not actually a thing you can differentiate, say with respect to time or something like that, in a way that is calc rigorous. This is where we have to take the physics cheat of saying that the D's are really tiny deltas, and then we're just saying this is a small heat transfer, and then it's all okay. So there's a little bit, if you ever need to integrate this, you actually have to just think of it as a sum. But here we're not going to have to worry about that because this is an adiabatic process. Since an adiabatic process, this term is 0 anyway, so I can just let it go. And I get that dE therm is equal to dW. All right. So this would be, and since E therm is NCVT, this will be NCV dt. And since W was equal to P delta V, that's just going to turn into minus P delta V. This is going to be minus P dV. All right. Now, in order to get this, the problem is that the pressure depends on the volume through the ideal gas law. So we'll have to go back with the ideal gas law here. So that says PV equals nRT. So I'm going to rewrite this as P equals nRT over V. All right. So we can, with that for P, I can put that into here. And so substituting that in, I can now write NCV dt equals minus NR over, minus NRT, NRT times dV over V. Now if I divide both sides through by T and by NCV, let's see, so I can, we'll just cancel the n's. So dividing both sides through by T and CV, I get that dt over t is equal to minus r over cv dv over v. All right. Now, what I'm going to do, just looking ahead to what and these are capital C's because it's molar specific heat, so let me just make that a little more blatant there. So what I'm going to do now is I'm going to let, and this is just looking ahead to what the answer is, gamma, I'm going to define that to be the ratio Cp to Cv. And since the difference of these is just r, I can observe that r over Cv is equal to gamma minus 1. So I'm going to go ahead and put that in there, and that will make a little more sense. Now, now I have dt over t is equal to minus gamma minus 1 dv over v, and I'm finally set to integrate both sides. So I will integrate this from the initial to the final temperature, as long as I do the same thing from the initial to the final volume. So this gives me the natural log of T final over T initial is equal to the natural log of V initial over V final to the gamma minus 1. So this will give us T final V final to the gamma minus 1 equals T initial V initial to the gamma minus 1. So that's one relationship between the initial and final states of an adiabatic process. And if we use that PV equals nRT, and so we can say that T is equal to PV over nR and do some canceling. You can also rewrite this as P final, V final to the gamma equals P initial, V initial to the gamma. And that was the result that I had promised from before. Now, for a monatomic gas, we saw that roughly, if you go ahead and plug in the values for monatomic gas, what you'll get is that gamma is 5/3 if it's a monatomic gas. We'll also be showing or arguing in a bit that it's 7. You can argue in a bit that it's 7/5 if it's a diatomic gas. And that's 8/6. And I'm cryptically leaving it like that rather than reducing it to 4/3 if it's a polyatomic gas. So more than 2 atoms. Atomic gas. So we'll justify those numbers later. But now what I would like to do is just finish up our thoughts of heat transfer by taking a look at the heat transfer processes. And to this, in this vein, I am going to be thinking about baking cookies. Now, it is an indisputable fact that the best cookies in the universe are chocolate chip cookies. And so we want to think very carefully about how we can make the best possible chocolate chip cookies. So there's the oven with the glass for the oven. So this is the Calorod if you have an electric oven, and you'll get better results if you bake electric versus gas because you're not releasing water from the combustion of the natural gas in the air. So here's your rack. Here is your cookie sheet. And then sitting on the cookie sheet are your chocolate chip cookies. Now, to have proper chocolate chip cookies, what you want is the tops to be still a bit soft. You want the chocolate chips to be melted but not completely gone. That's why it's preferable to chocolate chunk, where you never really get a good melt. And you want the bottom still to be nice and crisped up. And it turns out that all three of the processes of heat transfer are involved here. So the first of these is the reason why the bottom of your cookie crisps up more than the top is because the bottom of the cookie is in direct contact with the cookie sheet. And this is the most efficient form of heat transfer, conduction. Now, what's going to be responsible for the bulk of the rest of it, cooking up the tops, but not as thoroughly as you had cooked up the bottoms of the cookies, is going to be convection. So the cal rod here is going to heat up the air in the oven, and that's going to, whoops, that color is too similar. So I guess we'll use a green. There we go. So the heated air, the cal rod will heat the air. And it'll set up a convection cell where the air is tumbling around, kind of in a donut shape, if you extend this out into 3D, where the air is falling down in the middle and coming up the sides. This is assuming you don't have a convection oven. If you have a convection oven, the convection process will be enhanced, because instead of just rely on just natural changes in thermal energy causing the air to move around, you use a fan to push the process along. That's why you can cook at a little lower temperature with a convection oven. And it'll tend to cook the tops more of whatever it is. Sometimes that's desirable, sometimes that's not. But anyway, this is our second most efficient means of heat transfer, convection. And so this is heat transfer via a fluid. And remember, a gas can be a fluid just like a liquid can. So the hot air falls down on top of the cookies, cooks the tops. Because it's less efficient, it won't crisp up on the top, and you'll only get a partial melt on the chocolate chips before the bottoms get nice and crisp. So that's why you want to pull it out early. Now, for the reason why every recipe tells you to spin the pan around halfway, and I'll give you a tip here to avoid doing that, so you don't just dump a whole bunch of hot air out that you have to reheat, and then that messes with the convection. And the big tip here is that you'll want to clean your oven. And again, I've got bad choices of color here. So the third method is radiation. So this is the least efficient. And so this is by light, photons. So if you notice that the cal rod is glowing a dull cherry red, it's actually glowing pretty bright in the infrared, but you don't have infrared eyes. So about 85% of the heat that's being transferred as light energy is in the infrared, and 15% is the bit you can actually see. This is why most countries have now pretty much banned the sale of incandescent light bulbs, is because you had to use a heck of a lot more energy just to make the visible light, whereas compact fluorescents and LED lights can make pretty much all of their light in the visible, and so you can use an awful lot less energy to make the same amount of visible light. So anyway, so this is radiation via photons. However, what happens is the walls of the oven have gotten heated up. This is why it's important to preheat the oven. So photons get absorbed and they get re-radiated out, and they're bouncing all over the place. However, if you've got like a grease splatter or something, or too much pizza cheese that's melted onto some bit of the oven, that'll change the efficiency with which you can absorb and re-radiate the photons. And so this means that as a result, some parts of the cookie sheet will be getting hit with more mostly infrared photons, and others will get hit with less. And this will cause some of the cookies to have their tops cook up a little quicker than others. That's not desirable. So a lot of recipes will say spin the cookie sheet halfway through, basically in order to swap up the spots where the photons are more likely to strike with areas where they were less, and hopefully even all that out. On the other hand, if you do a good job of cleaning your oven, and most ovens nowadays have the self-cleaning cycle, so just use it, you can ensure that you're equally efficient everywhere on the oven walls, and then you'll have a nice uniform bath of photons, and then there will be no need to open up the oven and spin the cookie sheet around, thus causing a whole bunch of hot air to fall out of the oven that has to get reheated, which messes with the whole baking process. Certainly don't want that. And that's probably even more important for things like the Thanksgiving turkey, because that can definitely cause some parts of the turkey to get crisper than others when you're usually trying to aim for the whole bird to be roughly the same. All right, now it turns out that two of these methods of heat transfer, conduction and radiation, we can come up with nice mathematical models for. Convection is a royal pain. So I'll just say this about convection, and then I will go into looking at conduction and radiation. So with convection, to model convection is really hard, and you pretty much have to resort to computational fluid dynamics for most of it. There are other rules of thumb you can use, but for the most part, you're going to have computers think really hard about this stuff for you. And so I'll just give one fun result. It's Guinness beer, a company that was making available as a service doing CFD calculations. Just figured they had to do something real world, and so they went ahead and thought about what happens with a pint of Guinness. And one of the things that you'll see pretty much everyone note about Guinness versus other beers is that you tend to get a fairly persistent head, although there's usually a bit of a dimple in the head in the middle. But you get this fairly persistent head. And then if you look at the bubbles in the beer, everyone was swearing that the bubbles were falling down instead of going up like they do in most beers. And this actually turns out to be the case. What the people who did the modeling were, I'm sorry here, you notice that there's a crown in the head, unlike other beers. What the people who did the computer modeling found is that the way the convection cell works in Guinness is when you got the glass sitting on the bar, you'll have a heat transfer into the glass like this, or going in like this. And it turns out that instead of going up like this, in the case of Guinness, convection cell runs the other way, like that. Now, this is just kind of true. Whoops. My bad there. Let's get those arrows correct. And it goes like that. And so in most beers, this is true for most beers, but the thing is with most beers, they aren't that viscous. And so the bubbles can still continue to propagate their way up, despite the fact that the beer is convecting the other way around. Not so Guinness. With Guinness is a pretty thick beer, so it's pretty viscous. And so it turns out that the convection cell is strong enough to drag the bubbles down with it. So the bubbles actually get dragged down the middle, brought up the top, and they finally emerge to the surface in the middle of the beer, which is why you get that crown on the top of the head of Guinness. And it's not an optical illusion. The bubbles really are going down, but they're trying to go up, but the fluid is going down faster than the bubbles are going up in the fluid along the edges of the glass. In the middle of the glass, they are going up. So that's about what I have to say about convection. It's really hard, and we'll just leave it at that thought. But for conduction and radiation, we can come up with nice models for this stuff. So for conduction, let's say I've got some reservoir being maintained at T hot, and some other reservoir here being maintained at T cold. And then I have some material in between the two. So we will be continuously transferring heat through this material. So say if this is your house, this is the inside of your house, this is the outside of your house, this is the insulation in between. And on a winter day, the inside of the house is usually being maintained by a furnace at a high temperature, and it's being maintained at a cold temperature by just the fact that there's so much air outside the house. This is an example of something called a steady state system, where the temperatures are being maintained by an input of energy, in this case, running your furnace. Now, it turns out that we can model the rate at which the heat is being transferred. So we'll just say Q over delta T. So this K here is the thermal conductivity. And just like with fluids, where you can move more liters of water per second down a fat pipe than a skinny pipe, because there's more molecules in a fat piece of material than a skinny piece of material, we can have a greater rate of transfer of heat as the area increases. However, like we saw with the salt crystals in a previous video, the longer this is, the more intermediate collisions you need to have. So that decreases the rate at which we can transfer heat. So it goes inversely as the length. And then there'll be times the difference in temperature. Now this isn't a T final, T initial. This is a T hot, T cold. So just to do a quick example of that, let's say that I had an aluminum bar that I'm maintaining at one end at 100 degrees C. The other end is at 20 degrees C. We'll say that the cross-sectional area is 1/10 of a square meter, and that this is 1/10 of a meter long. What is the rate at which we are transferring heat? Well, that will be, so Q over delta T for this one will be the, K A over L, T hot minus T cold. So K for aluminum is 240 watts per meter Kelvin. So the cross-sectional area is 0.1 square meters. The length is 0.1 meters. I just did that to make the numbers as clean as I could. 100 degrees C minus 20 degrees C. Now here, once again, it's not a mistake to convert to Kelvin if you want. It's just a needless step because since this is a difference in temperature, the difference in the Celsius readings will give you a Kelvin difference. Anyway, plug it all through and you will get 19,200 watts, or if you prefer, joules per second. So, doing pretty good here. Now, just as an aside, a lot of times you'll see thermal conductivities restated as thermal resistivities, which is 1 over that. That turns out to be related to the R factor of insulation. But it's all in British units and it gets really weird. So, but anyway, big R factors mean low thermal conductivities and also mean thicker, so bigger L bats of insulation. All right, then we'll take a look at black body radiation. So I'll have to leave it for a later treatment to get into why it is that hot things emit light, but they do. And so all I can do right now is just state that the rate at which energy is emitted or absorbed is Q over delta T is equal to E sigma A T to the 4. This is the Stefan Boltzmann law. Where E is the emissivity of the material. And this is just a number and it runs from 0 to 1. If it's 0, it is a perfect reflector. And if it's 1, it is a perfect absorber. General rule of thumb is darker colors are closer to 1, lighter colors tend to be closer to 0. The sigma is the Stefan Boltzmann constant, which is 5.67 times 10 to the negative 8 watts per square meter Kelvin to the 4. This is one that you can actually kind of remember if you're thinking of somebody counting off a dance troupe. That's 5, 6, 7, 8. Well, maybe that helped you to remember it anyway. A is the surface area. And T is the absolute temperature. So here you gotta work in kelvins or Roncanes. So usually you are not, since you're not always just sitting in at absolute 0, the net transfer will actually be the difference in the 4th powers of the object's absolute temperature and the temperature, the absolute temperature of its surroundings. So a couple of quick notes here. This is why, for instance, in the summertime, people tend to prefer wearing lighter colored shirts rather than darker colored shirts, unless they've got a serious fashion reason for the darker colors. This is because with the higher emissivity, you do a better job of absorbing radiation from the sun, and that transfers more heat into the body. With a lighter colored shirt, the emissivity will be lower, which will reduce the rate of heat transfer. By the same token, this is also done in a lot of cars, especially cars that have glass roofs. They actually have very cleverly chosen layers of material that, although the object looks clear, in the infrared, where most of this transfer is happening, the emissivity turns out to be a bit of a train wreck. And so the car doesn't do a very good job of emitting or absorbing heat. So in the summer, the light shining in from the sun isn't baking the car. And if it's in the winter and the heat is trying to escape the car, it's also doing a bad job of radiating it out to the environment. So anyway, important to note is that the difference in the fourth powers is not the same thing as the fourth power, as the difference raised to the fourth power. So just be super duper careful when you're doing that. Just play with some numbers to convince yourself if you don't believe me. But it'll create an enormous difference. So just to do an example here, let's say that we have an ideal black body in space. Now, it turns out, so the ideal black body is telling us that the emissivity is equal to 1. And by the way, the notation isn't consistent that you use E. Lots of books use all kinds of letters for the emissivity, so you'll just have to pay attention to whatever any particular book uses. And at first you might think that this is kind of ridiculous, but this is why a lot of satellites get coated in gold. When you're out in space, although conduction and convection would be better, they're not available to you. You're not in air anymore and you're not touching anything, so radiation's all you got. And it turns out that gold has an emissivity that's pretty darn close to 1. So if you coat your satellite with a very thin layer of gold, you get this emissivity up to pretty darn close to 1. So this isn't as unrealistic as it sounds. Now the in-space bit is telling us that the temperature of the surroundings is 3 Kelvin, roughly. This is actually due to energy left over from the Big Bang. So let's say it's at 50 Kelvin, so it's pretty cold. And let's say the surface area is 2 square meters. Let's find the rate at which we are dissipating heat. So because we are being surrounded by something, we have to use the relationship where we take into account the difference in the fourth powers. So we'll go ahead and say the emissivity is 1. Stefan Boltzmann constant is 5.67 times 10 to the negative 8 watts per square meter, Kelvin to the 4, 2 square meters. And then we'll say 50 Kelvin to the fourth power minus 3 Kelvin to the fourth power. Now, once you take the fourth powers of these, you'll find that the fourth power of 3 Kelvin is a heck of a lot smaller than the fourth power of 50 Kelvin. So being this fussy usually only matters if there's only a small difference in absolute temperatures. But it doesn't hurt to be careful about it. At any rate, it's 0.709 watts. We're not exactly belching the heat out here. And so it does show us that even with an ideal black body surrounded by as cold as we can get, you're not really putting heat out. So when you design satellites, you got to be careful about how much heat you produce and what your strategies are to radiate that heat out. Alrighty, so going forward, we will start to think about deriving the ideal gas law. So we will catch you in the next videos. Catch you later.